All right. We're smart people. We can figure this out. Polynomial function. So I'm teaching polynomials to my grade 9s right now. They're just learning what they are. You guys are going to learn how to graph them and create equations for them. So you've done polynomial functions with degrees of 1. Those would be your linear from grade 10. Last year you graphed squared functions, so that's your parabolas. And this year we're going to be doing cubic, quartic, quintic. We can do all kinds. So we're going to go beyond the squared this year. It's not that big of a stretch. If you guys can graph linear and you can graph parabolas, you can do this, no problem at all. I probably should erase the board, eh? So the deal with polynomial functions is that the exponent has to be a whole number. Has to be a whole number. Key feature. It can't have any other weird things with it. It can't have absolute values. It can't be a root function. It can't be any of those things. So it has to be just a standard whole number. You need to have a variable in it. Now I said x, but that's not true, any letter. So it needs to have a variable with the exponent. And the coefficients a to f are real numbers. So they're not the square root of -2 or anything like that. Okay, end behavior. This one I'm going to talk a lot about. End behavior is important. When I say end behavior, what I'm looking at is where does the graph end? What is it doing? What quadrants is it ending in? Is it, if I were to graph a linear function, if I were to graph y equals x plus 2, can you guys tell me in what quadrants does the graph end in? So you got to visualize this. Let's visual.
1 and 2.
I'd give you 1. Definitely 1. But this is going to go like that, right?
Oh, yes.
So since it's linear. So what's the end behavior on this graph? Ends in quadrant 1, ends in quadrant 2. Or quadrant 3. Does that make sense to everybody when I'm talking about end behavior? That's what I'm talking about. So this one has end behavior in quadrants 1 and quadrant 3. So what's happening is x becomes, and I put absolute values around x, what's happening when x gets really positive? And what happens when it gets really negative? And that's what we're talking about. So really negative would be quadrant 3, and really positive would be our quadrant 1. So as x gets really positive, increases in the positive, we're going into quadrant 1 there. But when x gets really negative, we're going into quadrant 3. That's end behavior, and that's important. Because we're going to know that for all the types of polynomial graphs. Okay, let's look at this. Okay, which functions are polynomials? Justify your answer. Okay, what does justify mean? Justify's on that board there. What does justify mean? Peyton, you're the closest. I don't have glasses on.
Show reasons or give facts that support a... I can't see what that says.
Okay. Anybody can finish that sentence? So, give reasons, show facts. Everybody's like, none of us can read, is what I've just learned about the class, including me. Thomas got the furthest, the rest of us not so much. So when we say justify, we're looking for either math to show me answers or words to show me answers. Okay, discuss the leading coefficient and the constant term of each polynomial function. This guy right here, is it a polynomial function? How come?
It's a radical function.
It is. You guys remember this from grade 11?
Yeah.
Can you change the radical into a rational exponent? Yeah, you can.
Put x to the power of -1
Nope. That would put it over 1. When it's a root, what kind of root is it, ladies and gentlemen?
Square root.
It is a square root. What's the index on that thing?
2.
2. What's the exponent on the x? 1. Is that a polynomial function? No.
What?
Why is it not a polynomial function? What do the exponents have to be in a polynomial function?
Not like that. It gotta be a whole number.
They have to be a whole number. Is 1/2 a whole number? Okay. Good job, everybody. Okay. 3x to the exponent 4. Is that a polynomial function?
Yes.
Yes. All right, so what's the leading coefficient on this one? Do you guys know what I mean by leading coefficient?
3.
Okay, yeah, definitely 3. So, but that's a coefficient. What does leading coefficient mean? Anybody know? You guys are like, I don't know. Why don't you tell us? The leading coefficient is the coefficient on the term that has the highest exponent. This one only has one term, so the leading coefficient is the coefficient. Do you guys remember what the degree means? I just did this with my grade 9s. The degree?
Yeah, to the power of 4.
Okay, so in this case it is to the power of 4, so the degree is 4. It is the highest exponent in a polynomial. Everybody okay with that? And what else was I supposed to hit? Positive 3, leading coefficient. What's my constant? Is there any number added to that?
No constant.
So there's no constant. Or we could say the constant is 0. Because what does the constant tell us? What did the constant tell us here?
Starts at 0.
What do you mean by starts at?
Like the point starts at 0 in the y.
Okay, the y-intercept
Yeah.
is the constant,
Yeah.
right? Just like this one, when it's plus 2, the y-intercept is here. All right, absolute value of x. I'm not even going to make you guess. It's not.
It's a crap.
No, it's not.
Well, it never crosses the x.
True story, it doesn't cut the x-axis,
Yeah.
but it's a v. Remember absolute values, they make that v, they don't have the nice smooth bottom curves, so we can't call them parabolas. This guy's different because there is math attached to it with those type of brackets. Those absolute brackets cause some math to happen that makes it not a polynomial function. It takes away its ability to do things. Okay, what about d?
Yes.
Yes. All right, so let's go through it. What is the degree?
3.
Degree is 3. It's the highest exponent. Leading coefficient?
2 or 4.
2. So we're looking for the leading coefficient is the coefficient on the term that has the highest exponent. And then what's my constant?
-1.
Did I miss anything there? No, I think those are the 3 things. What about this guy?
No.
How come?
It's just not.
It's just not. Don't ask me questions. I could write it like that. That's that negative exponent in there. So with that negative exponent, we know that a polynomial needs to be a whole number, no negatives in there. So that's why that one doesn't qualify. The last one, hopefully you're all saying yes. What's the degree?
5.
5. Leading coefficient?
-2.
-2. Constant?
4.
4. So the good thing is, though, guys, in this unit, you're not going to be dealing with the harder graphs like the radicals or the reciprocals. That's chapter 2. This is chapter 9, right? Absolute values was something that we did in grade 11, but if you look on that exam I just gave you, it is an absolute value question. Okay. This whole page is about end behavior. This whole page is about end behavior. All right. If you have a constant function, this means a degree of 0. So this would be like y equals 2, y equals -1, whatever the case may be. Your end behavior is going to extend horizontally. Your range is only going to be a single number. Like this one is f of x equals 3, so y equals 3. Your end behavior extends horizontally. It could be down here. So this one is 1 and 2, but this one could be 3 and 4. So constant functions are a little bit different. Number of x-intercepts, there would be none. There would be none. Or infinite, because if it was y equals 0, it would lay on top of the x-axis, and every single point would be an x-intercept, and that's just silly. We don't do a lot with constant functions in grade 12, but it's good that you just know about them. Okay, linear, grade 10. Welcome back. Number of x-intercepts. Now, degree of 1. It's an odd degree. It's odd. I'm just going to point out, I'm going to slide this up for a second. Cubic functions also is an odd degree. Quintic functions, also an odd degree. Do you guys see the connection there? 1, 3, 5. What would be my next one? 7, right? 9. So odd numbers are odd degrees. All right. Okay. So we have a positive leading coefficient here. Positive leading coefficient. If it's a positive leading coefficient, we're going to write this down somewhere, but I'm not sure where yet. If it is a positive coefficient, you're going to have end behavior in 1 and 3. If it is a negative leading coefficient, your end behavior will be in quadrants 2 and quadrant 4. But you know this. You know this because you've graphed a million linear functions. I'm going to go down to cubic for a second because it's not another odd degree. It's a positive leading coefficient, so your end behavior is in 1 and 3. Anybody want to guess if it's a negative leading coefficient? If it's a negative leading coefficient? 2 and 4. All right, let's look at that quintic function there. It's a positive leading coefficient. Positive leading coefficient. What's my end behavior? 1 and 3. If it was a negative leading coefficient, what do you think it would be? 2 and 4. So what do you know about all odd degrees? If it's a positive leading coefficient, they're going to end in 1 and 3. If it's a negative, they're going to end in 2 and 4. What's my domain for any of these graphs? If I'm doing this.
Negative infinity to positive infinity.
Okay, what's my range?
Negative infinity to positive infinity.
Uh-huh. So whether it's linear, whether it's cubic, whether it's quintic, positive, negative infinities on both the domain and range. Okay, now we're going on to even functions. Even functions. So an even degree, so we're on a quadratic. You guys have lived a life of graphing these. If the leading coefficient is positive, which way do we know the graph opens? Up. So what are my end behaviors?
They're going up.
What are my end behaviors? What quadrants?
Quadrant 1 and 2.
Quadrant 1 and 2. If my coefficient is negative,
Quadrant 3 and 4.
3 and 4, my parabola opens down. So a negative leading coefficient ends in quadrants 3 and quadrants 4. That would be the exact same thing for this even function, the quartic function. If it has a positive leading coefficient, it's going to go 1 and 2. If it's negative, it's going to be 3 and 4. So if you know how to graph a parabola, you have a really good idea already of how to deal with those quartic functions, even though you've never ever seen one before. Okay, those are all the end behaviors. I want to tell you one more thing about these. We're going to talk x-intercepts. So zero degree function, degree of 0, 0 x-intercepts. Linear function, so degree of 1, has 1 x-intercept. Quadratics, I could have up to 2. I might not have 2, I might have 1, might have 0, but I can have a maximum of 2. Cubic functions, I can have a maximum of 3. I might not have 3, I might have 1, I might have 2. You'll always have 1. You won't have none. Quartic functions, again, 0, 1, 2, 3, or 4. If it's a degree of 4, you have a potential of 4 x-intercepts. So if it's a degree of 5, guess how many possible x-intercepts you can have? Hopefully 5. Okay? So you might not have full 5, but they might be repeating, so you wouldn't see unique ones, but it's pretty exciting stuff. So if you know how to graph a linear, which you do, you're a smart person, you can graph all the rest of them. Or you at least know stuff already about them. Okay, this just summarizes what we talked about it. Okay? If you have an even degree, graph extends into quadrants 1 and 2, where the leading coefficient is positive. Quadrants 3 and 4, when the coefficient is negative. Even degrees. The y-intercept corresponds with the constant term of the function. So, y-intercept is the constant term of the function. That's why those are important. The degree of the function is the maximum possible number of x-intercepts. The domain is all reals. The range is dependent on the maximum or minimum value of the function. So this one has a restricted range. There's something you need to do there. So this one we're going to have to think about before we do it. In an odd degree, if we have a positive coefficient, it's 1 and 3. If it's a negative coefficient, it's 2 and 4. But we just went all through that. The y-intercept corresponds to the constant term. Same thing as in an even degree. The degree of the function is the maximum number of possible x-intercepts. Same as above. The domain, all reals. Range, all reals. I don't have to think about that. I know anything with a degree that's odd that's going to be XER, YER. I'm done. Don't have to even think about it. There are no maximum or minimum points. Now, for those of you continuing on to calculus, you guys are going to learn how to graph these points with the relative max and mins. We're not going to get into that in grade 12 pre-cal. We're going to talk mostly about end behaviors, x-intercepts. When you come to calculus, we're going to learn a little bit more about where those specific points are. It's not hard. It's first and second derivative. It's easy peasy. Okay, that's a lot of me talking. All right, identify the following characteristics of the graph of each polynomial. The type of function, whether it's odd or even, the end behavior, the number of possible intercepts, whether the graph will have a max or a min, and the y-intercept. And then match the functions with their graphs. Holy Hannah, that's a lot of math to do. Okay, let's look at graph A. We're looking at graph A here. What do we know about graph A? It's an odd graph. So the degree is odd. And how did you know that? You're not wrong, Prince, but how did you know that?
Because it starts in quadrant 1 and it goes into quadrant 3.
It's doing one of these. It's doing a ta-da. Okay, so it is, as soon as my arms are separated, it is an odd function. What do we know about the leading coefficient of this? Is it positive or negative?
Positive.
Positive, because it's 1 and 3. 1 and 3 is positive. How many intercepts do we have here?
Wait, the other one?
We're still doing this one. Pause, x-intercepts. Let's do x-intercepts. 2?
Yeah, because the other one's just touching it.
We'd still call that an x-intercept because it touches the x-axis.
Is this a cubic one?
Could be. And then we have our other guy over here. So we have these two x-intercepts that we're seeing. You guys are gonna, yeah. Okay, what else am I supposed to find? Whether the graph has a max or min. Is there a max or min to a cubic function?
No, there is none.
There is none because it's infinite in either direction. So in calculus, we would say no absolute max or min, but we can then talk about a relative max and a relative min. So just know we're going to go a little bit deeper in calc with this. So if you're like, what does this all mean? There is another layer to it. And then the y-intercept. Where do you think that y-intercept is? I think it is at 3.
Our graph doesn't even say numbers.
It doesn't. It says 12 way the heck up there and 1 way the heck down there. Do you guys know how I picked 3? I looked at my equations. This one has a y-intercept of -4, +3, 0, and -12. So this is probably it. Okay. So with deducting that, if this crosses at +3, this one has a degree of 3. We said that this is an odd function. B matches with graph A. All right, let's look at graph B. What kind of degree is this? Odd or even? It should be even because my hands are up in the air. We've got a field goal. So 2 hands facing in the same direction are going to be ever. How about even? How many x-intercepts?
3, 4, 3, 4. I can see it.
Wait, there, there's 4.
So 1, 2, 3, 4. Ooh, I forgot to do my leading coefficient. Is that positive or negative? Which way is my graph opening?
Up.
Up. So what do we know about the leading coefficient?
It's positive.
Positive. Think about your parabolas, right? This is not new. And x-intercepts, we said we had 4. And then what else? Max or min?
There's a minimum, but
There is a minimum.
there's no max.
Okay, what's my minimum at? I can't tell either. So we would say this would be my minimum here, right?
Yeah.
Okay, so my minimum isn't my y-intercept. It can be, but it's not always. So, I know I crossed somewhere down here for my y-intercept. And if I were to look at the equations, where do you think I cross? If this is -30 down here. -12. All right, so that means that D, equation D, belongs to graph B. And just to double check, we have a positive leading coefficient. We have a degree of 4. So you know how like when you were learning this in grade 9 and we always said like put them in order, put your exponents from highest to lowest. There is a purpose to that. It makes it so much easier that you're not looking around in the equation to do it. Okay, graph C. Graph C. What's my degree?
It's odd.
It is odd. What's my end behavior? What am I doing in this one? I'm 2 and 4, right?
Negative.
So my LC, my leading coefficient, is negative this time. How many x-intercepts? 1, 2, 3, 4, 5. Max or min? None. And the reason why we don't have a max or min is because the end behavior goes on forever. We have no absolute max, no absolute min. Where's my y-intercept?
0.
I would say you are correct. At 0. So if I go back to my equations up here, p of x doesn't have a constant, so that would mean it's 0. It has a negative leading coefficient, and it has a degree of 5. So C would match, C would match C. Okay, so what do you know about the last one?
Degree of E and LC is negative. There's 4 x-intercepts.
Yeah? It is A, yes. There's only one left, but do you know why? This is a leading coefficient that is negative. X-intercepts, I have 1, 2, 3, 4.
I have a question. There's a quadratic formula, but is there like a cubic formula or something, or does that not exist?
It doesn't exist, but what we're going to do is we're going to do synthetic division, and we're going to teach you how to factor these crazy kids that are huge. And in the end, you'll get down to maybe a quadratic that does require the quadratic formula, but there is no formula that you can pump all these into and be done with. Your life has gotten complicated. I could make you do long division if you wanted to, but synthetic division is a little bit easier.
I love long division. Super easy.
Okay. That's fun. All right. A bank vault is the same shape as a rectangular prism. Volume is related to the width, W in meters, of the vault doorway by the function of that. What is the volume in cubic meters if the doorway is 1 meter wide? Super easy question, folks. Super easy question. We have a rectangular prism vault. It's given us the volume formula.
I have one question.
Yeah.
Do we multiply the 13 and then 1, or do we just put 1 to the square root, 1 to the root of
1 to the exponent 2?
Yeah.
Yeah, you do 1 to, well, I mean, again, it's not like, I'm going to show you all the steps just because that's the crazy person I am. But what's 1 cubed?
1.
Right. What is that? Can you do it without a calculator? How much? 140, I would agree with you. How'd you do that in your head? No, I know you did it in your head, but what math things did you think about in your head? You just added, so you did 1 plus 13 is 14, 14 plus 54 is 68 plus
Well,
72.
It's very easy, and
Okay. Did anybody add up the tens first? Like, did anybody go 10 plus 50 plus 70?
I did
And then add all the ones together?
I just did 14 plus 54, 68, 68 plus 72, 103.
You just did it in your head?
Yeah, it's starting from the left side though, because 1 plus 13 is very easy.
Okay.
13 plus 54 is pretty easy.
True. Okay, am I done? Because if you leave it like this, I'm going to deduct a half mark. What am I missing?
Meters.
Meters cubed, because I'm in volume. What is the least volume of the vault? And what's the width of the door for this volume? And why is this situation not realistic? What's the least volume you could have for the vault?
How do you calculate for that?
Because if you graphed this, if you went ahead and graphed this, your y-intercept is going to be at, if my width is 0, what's my volume?
0.
Nope,
72.
72.
Yeah, makes sense.
So why is that unrealistic?
If it has no width, it cannot be 72 cubic meters.
So sometimes what you need to know is the polynomial function will model the situation, but you need to be smarter to put the restrictions on it. Does that make sense to everybody? Like, you have to know more about the context of the situation, and we all know we can't have a width of 0. I think it says like particle physics? Nuh-uh. Okay.
Oh, I have a question.
Yeah.
How do you mathematically solve for a square root?
How do I solve for a
Yeah,
square
like
root?
how do you do it like?
Oh, okay, like just like, is there a formula instead of the button on my calculator? I don't know. Like, I know what it is in theory, right? Because you are undoing a squared exponent. So it's the action of undoing it, but I'm not sure what the longhand way would be of doing that.
Okay, I'll look at it later. I was curious about that.
No, that's a fair question. Ladies and gentlemen, that's your first lesson in chapter 3.